It's only yesterday that I'm the co-chair of this thing. Well, I wanted to know, well, what are the responsibilities of the co-chair? And basically the answer was, anything that John doesn't want to do, I have to do. So we got to the point of, well, somebody's going to have to say something about integrating all of this stuff. And they pointed at me and said, that's you. So here I am. I'm worrying about this. So let's see what we've got. That says who I am. All right. Okay, we're going to talk about an overview of integration and some categories and types of activities, and the fact that it's going to be non-trivial. Let me give you a thought to start with. Suppose you are building a building here in Oak Ridge. Now, I'm not talking about a high-tech building. I'm talking about, 4 or 5 story building that's, it's got elevators and doors and windows and stuff like that. It's pretty standard. All right, if you have an engineer and an architect that have done this before, they can say, all right, these are the things that we'll have to do, and we're going to have to, first we've got to dig the footings and we've got to pour concrete, and they know how to integrate all this stuff because it's defined beforehand. If you've been watching what people have been talking about, you will have noticed that we don't have a defined beforehand anything. We're talking about a program where we define a lot of the things as we go. A lot of it is thinking of new things, testing them, and then building them and integrating them. So the definition of integration isn't the same, except in a very loose sense, of integration of a building project where you know what you're doing. Okay. I'm not actually going to do this part because Mark Uran tomorrow is going to talk about this part, and it's good. Because that's the hard part. I'm going to give you the nice, what did we used to call it in grad school? Arm waving.
Give me the hook.
That's Mark Uran over there who's complaining. You see, part of the reason that's good is because he's actually done this kind of thing. I'm just, I'm the co-chair. I got stuck with it. All right. Well, let me tell you about what a fully integrated vision might be. Did you hear about the restaurant on the moon? The food's great, but there's no atmosphere. Okay, that was an American Legion magazine, and I couldn't resist it. Okay, what's our mission objective? We heard about this a little bit earlier when we had all the people here saying, well, if we don't know what we're doing, how do we decide which things are good to do it? Well, here's a start. Launch for Mars before 2030. Establish a permanent lunar presence by 2026. Conquer and occupy Cis-Lunar space by 2024. Okay, you could make that 2025 and a half or, but this gives you a start. Okay, I'm going to be using the word technology loosely to mean everything that I'm talking about. Now, one thing, we haven't discussed every needed technology. I haven't heard anybody talking about no, we don't have screen doors, but airlocks. You probably are going to want to have airlocks. What we have talked about are other things. We've talked about things that we thought there might be a breakthrough possible in this area. The ones where we thought well, we either know how to do it or it's going to be an incremental improvement over the years, we didn't bother talking about here. So there's a bunch of stuff that's necessary that we hadn't talked about at all. It doesn't mean we don't know it is necessary. It just means we weren't interested. Now, we don't have time to talk about everything. Now, there's something that you've heard about in here. We've had both competing and cooperative technologies discussed. But you may have heard somebody ask about roles. This is a book, one of the first books of science fiction for kids that was in my age, Robert Heinlein's rocket ship Galileo. He had it nuclear power to use thorium. It took off from Earth, and we know that that's not going to happen. Okay? Earth launch, basically we're going to do chemical powered, not because it's necessarily the only way to do it, but because we're not going to get as much political flack doing that. You achieve orbit, and you can use it for prepositioning non-human cargo. Off Earth, we can do nuclear powered, and we can have human passengers on them. Notice that those could have been considered competing technologies, but if we say we've got differing roles for the technologies, all of a sudden they're synergistic. They're cooperating technologies. So part of the thing that we're talking about here is just getting the ideas out there. When we start talking about roles and what's costs and practical and what we need for things, then we get into the details of, okay, should we use this for that and this for the other, or don't bother with this, or, those are when we get into those details, but we don't have to yet. Right now, we just want to discuss and understand what's available. So our technology categories that I'm talking about: propulsion and transportation, power, which means production and collection, transmission, superconductors. Am I talking well enough to get into the microphone here? Okay. Materials and uses, that includes asteroidal and lunar regolith collection, additive and subtractive manufacturing, construction in space and on the lunar surface, environmental control and life support, space and lunar habitat and ecosystems in general. So these are categories of technologies, what I mean by what I'm calling technologies for this point. Now, integration. Well, we've got to integrate safety into everything we do. Now, safety may be one of those things that you say, there's always a little bit of risk. How much are we willing to take? But we've got to consider it that way. We can't just let it happen. We've learned to our pain that if you don't consider safety, it comes up and bites you. And that's not good. We've got to integrate infrastructure. We've got to integrate the testing of the technologies. That means the sites, the times, the purposes, the use cases, integration steps, selection and production. We've got to integrate computational systems. In the old days, when they were building this era, computation was basically adding machine and slide rules. Now we've got a lot more complicated computational machines, but we still need to worry about it. And we've got to integrate the environments and the activities. Okay, let's talk about integrating safety. There's terrestrial safety, because a bunch of the stuff we're going to be doing is going to be on the Earth before we ever get to space. There's going to be habitat safety, what you do in the habitat, spacewalk and construction safety, and travel safety. Now, those are just some sketches of different kinds of places where we need to worry about it. When you get into the details, it obviously gets hairier. All right, integrating infrastructure, vehicle systems, trajectory deconfliction. If you think about it, if we've only got one space vehicle going to the moon at a time, you have to worry about not hitting the moon if you didn't mean to. If you've got some work going on, you're going to have to worry about not hitting the other people that are out there as you go through. We've got activity deconflictions. This is just, a Gantt chart kind of thing. You've got to make sure that you don't have the same person scheduled to do something in two different places at the same time kind of thing. Okay, looking at the vehicle systems, there are going to be some commonalities with aviation. We're going to have multiple sources for the parts, multiple sources for the aircraft or spacecraft, multiple uses for aircraft and spacecraft. The first one is multiple users and then multiple uses. Multiple launch and recovery sites, multiple flight paths. Okay, so those are things that we ought to be able to learn a little bit about in our space deconfliction things, and it was mentioned earlier yesterday about a space management system. This is the kind of thing that if you're familiar with the management of airspace, you know that it can get quite complicated. Expect it to get quite complicated here. There extensive testing in cis-lunar space, and we need to worry about what not to do, like fail to upgrade control systems, fail to understand the dimensionality of the entire system. Now let's look at trajectory deconfliction. This one I had fun with. Okay, an awful lot of what we're going to be doing, we're talking about operating in the Earth-Moon orbit plane. Okay, so that's what that's supposed to represent. Now, most of the trajectories will be near that plane, but some will be in a third dimension. Okay, so that's what that's supposed to represent. We've also got hard bodies. Now, I've got this circle right here is an expansion of that circle, so that you could look at it magnified. Okay, we've got unpowered trajectories that might be running through our area of interest. These could be asteroids, or these could be just an unpowered flight path of somebody else's vehicle. We have powered trajectories. We have multi-component bodies where somebody says, this is mine, but it turns out that there are a whole lot of pieces that are separated, and you don't want to run into any one of the pieces. You've got energy, laser beams. Here's a laser beam. Okay, operating it here, it hits that surface and it becomes decoherent and not too dangerous. But if you're in space and you run a laser beam out, if it doesn't hit something, it's going to be a long time just as powerful as it was coming out of the operating end of the laser. So you've got to worry about that. Microwave beams, broadcasts, gases. Think about this. Suppose you're operating in one of these Lagrange points where things tend to stick around. The first time you use a coal gas maneuvering device, you put a few molecules out there and it's no problem. Okay, the next time you do it, no problem. Do that for 10 years with lots and lots of vehicles doing it. But think about doing it for 100 years. You know, if we're serious about this, that Lagrange point is still going to be the Lagrange point 100 years from now, 1,000 years from now. All of the things that we emit in there that don't go elsewhere are going to be still there. Space isn't going to be quite as hard vacuum after we've done, you know, a couple centuries of doing this. So you want to know about that. Okay, activity deconfliction, construction, transit, say trajectory. Testing, I'll talk about that in the next one. Okay, so this is the first one, sites. Going to have individual sites. Going to have common sites where you're going to be testing more than one kind of thing. Going to have times where you've got independent technologies testing, and then dependencies among technologies where you can't test this until that's been done. You've got relationships. You've got unrelated technologies, and that's great as long as they're not at the same place at the same time. But you've got competitive technologies and you've got complementary ones. You need to worry about integrating these things. Okay, this is one that I stole from NASA. This is the gateway thing. So this is could be a Cis-Lunar test site. So you see it's got a bunch of pieces there. Think about it. If we're going to be doing actual testing in Cis-Lunar space, that means people have a place to live while they're doing it. You've got to have equipment running around. You've got to do all that kind of thing. So this is one of the things that's been proposed. One of the other things we've talked about is asteroid stuff. So what if we decided we needed a storm cellar where we stuck a habitation module inside a bunch of regolith there that provided extra protection from radiation of various kinds. Well, would that make a difference? If this is close to that, it would have to be close to that to be useful. What does the possibility of kicking off all this dust and stuff that's on the surface of this do to your nice, clean gateway machinery over here? Those are kinds of things that may not be the first thing you think of, but somebody'd better think of them eventually. Okay, we've got ground sites. Okay, they're national lab ground sites, NASA sites, commercial sites, other nation sites, lunar sites. Okay, this is technology testing too. You've got to start talking about use cases. You've got to create the use cases where you say, this is why I'm testing something, this is what I'm trying to figure out. You've got to validate the use cases. And then you've got pairwise connections. You've got system of systems completion. Here's a good one, selections. Sometimes you're going to have to down select. You may have something that's wonderful, but it's not as good as something else. Or it's wonderful, but it's going to cost more than you can do. You might be down selecting to multiple approaches rather than single approaches. Depends on what you're doing, what's the right thing. And you've got to go into production. Computational systems. When I started with computers in 1966, 4K was all that we had. We didn't have Fortran. We had machine language. Now we've got, pretty powerful computers around. Probably for the initial deconfliction kind of stuff, a powerful gaming system might be adequate. But we might want to have 3 of them, so it's tell me 3 times so we believe it. But we're going to need predictive trajectories with tracking updates and all kinds of other things. Going to need large-scale project management. In the intermediate time frame, the things that we now call power systems will be more powerful power systems. Those power systems will probably be equivalent to a current small supercomputer. Again, redundancy. 10 years out, unless we've really done things badly, the computers will be a lot more powerful than they are now. We need to be planning for those upgrades. Okay, environments and activities, terrestrial near Earth orbit. Let's see. Okay, we've talked about these kinds of things. If we actually do them, they have to be integrated in as the right time comes along. But notice we have talked about the existence of the technologies. We don't have the use cases and the plans and the things to say, all right, here's how we would integrate them. So I'm just saying that we need to worry about those, not how to do it. Now here's our timeline. Okay, I've got Cis-Lunar over there, Lunar there, and Mars. And I've got wait, okay? Wait doesn't mean do nothing. What it does mean is we hadn't gotten to this point. This is the testing point. Well, test doesn't mean do nothing else. It just means I'm emphasizing the test part. And then use doesn't mean we're finished. It just means that we're well into the particular use of that part. And so we're talking, this is our nominal timeline that I started with. That was 2030 to launch our Mars mission, 2026 to be on the moon with a lunar base, 2024 to be saying we have conquered cis-lunar space. Okay, that's where that comes from. Now, conclusion. The technologies exist at various levels of readiness. That's part of the problem of saying how do you integrate it, because if we're doing it right, they're going to change their level of readiness over time, and then we can start integrating things that we can't integrate right now. They're going to be tested, proven, and selected, ultimately in space, management system. The International Space Station project proved that we can do this kind of complicated, complex management. And so I'm waving my arms and saying, we'll adapt that to this effort. So we'll use what we've learned. We need the will to do it. I think it exists in the corporations. I think it exists maybe in the government. But it's going to take some work to make sure it exists in the public. But we can do it. Okay, this is, we've got all that. Do you still want egg in your beer? Okay, so if you can't read this, Arlo is saying to Janice, they believe a moon of Saturn, Enceladus, has the essentials for life as we know it. Janice says, really? Shampoo, blow dryers, chocolate, Chardonnay? He says, I'm being serious. She says, you can dish it out, but you can't take it.